In this course, you're going to learn all the basics that you need to know about Apache Spark, like the architecture, what does the driver do, what does the executor do, how does it all come together, why is it so powerful, and when should you pick Spark over something else. These basics are going to be covered in the course, and then later on we are going to go into a hands-on lab to just talk about partitioning and sorting and how to actually have Spark read and write data. You will get a lot of hands-on knowledge in this course. Make sure to download Spark in the description below, and if you're interested in learning how to use Spark in the cloud, I highly recommend checking out the Data Expert Academy. You can get 20% off in the discount below. I'm excited to see you there. Okay, so Spark is a distributed compute framework that allows you to process very large amounts of data efficiently. Some of y'all probably knew that. It's kind of the successor to other technologies. If y'all followed any of like the progression of big data technologies, really everything started back with like Hadoop and Java MapReduce back in like 2009, and that's when those things were developed. And then we learned, and then they kind of transitioned to Hive, and then now Spark, and Spark is kind of winning. And like it's gonna be wild to see how long Spark actually sticks around, because it looks like it has a longer kind of technology curve than some of the other predecessors. But that's essentially what Spark is. We're going to go way more deep into the details of Spark here, but that's the idea. So I just want to talk a little bit about my history with Spark. So I learned Java MapReduce back in 2014 when I was working at Teradata. And then 2015 to 2017, I used Hive a lot at Facebook, a lot at Teradata. And then I remember in 2017, there was a big push at Facebook to adopt Presto, to switch Hive to Presto. But the problem with Presto back then, and still is kind of a problem with Presto now, is Presto does everything in memory. And so if you have an operation that can't fit in memory, Presto just fails. You can't use it. And so, and I worked in notifications at Facebook, so we couldn't use Presto. But I also didn't want to use Hive because Hive was slow and terrible. So like I was one of the very first early adopters of Spark at Facebook. I think I was like the third or fourth person to like create a Spark job at Facebook. And it was great. It was a slam dunk in so many different places in my usage, both at Facebook and further on in my career. I've tried all the different APIs for Spark, right? There's Spark SQL, there's DataFrame, Dataset, PySpark, Spark R. Like, I always joke with people about Spark R because people forget that you can actually write R code with Spark, and it's kind of crazy. But anyways, I attribute learning this technology as one of the main reasons why I was wildly successful in big tech, because I learned this framework very, very thoroughly, and I know all the ins and outs of it. And so it's been great. I've been using it since then, like since 2017 to 2023. So like so many years, like six years of just using Spark, and it's just gotten better and better and better since then. And yeah, let's keep going here. So why is Spark so good? There's a couple things. Spark is really good because it leverages RAM more efficiently and more effectively than previous iterations. So for example, like if you wanted to do a group by computation in Hive or MapReduce, everything had to be written to disk, and then written to disk and read from disk, and every single step had to be written and read from disk. And it made it very resilient. Like Hive and Java MapReduce jobs were very resilient, but they were also incredibly painfully slow. Spark was able to kind of short circuit some of that and minimize the amount of times that it needs to write to disk. Spark essentially only writes to disk when it has an operation that it doesn't have enough memory for, and then it will do this thing called spilling to disk. Generally speaking, though, like you don't want Spark to spill to disk. You want Spark to use RAM as much as it possibly can, and that's going to be where you get very effective and fast computations with Spark. Spilling to disk makes Spark, it essentially has Spark go back to being Hive, and it's, again, being kind of slow. So another thing about Spark is it's storage agnostic. Like you can read whatever you want, right? Whether it be a relational database, a data lake, a file, MongoDB, whatever you want to read, Spark can read it easily. Also, Spark has a massive, massive, massive community. And you don't need to use Spark with Databricks. You can use Spark with whatever technology you want, and it works great. So that's pretty much what is going on with like why Spark is so good. When is Spark not so good? There's going to be, I think, 2 cases when I would say that you don't want to use Spark. The first one is similar. It's a very similar guidance to what I said about Flink. Was if you're the only one on your team that knows Spark, then like you probably shouldn't use Spark. You should, or you should teach your team so that you can have better maintenance and better reliability, and you can distribute responsibility more effectively. And also, your company might already use something else. Like a lot of companies bet heavily on BigQuery, or they bet heavily on Snowflake, or they bet heavily on another kind of technology that isn't Spark but also works. And in those cases, like it's better to have 20 BigQuery pipelines than it is to have 19 BigQuery pipelines and 1 Spark pipeline. Like it's just like homogeneity of pipelines matters a lot. I've used that word a couple times in some of these presentations, and that's when like you don't want to bring in Spark in those cases. You want to just use what the company's betting on. Okay, so how does Spark work? So I like to use the analogy of Spark as like a basketball team. So the basketball team has 3 things in it. It has the plan, which is the play that the basketball team runs. The driver is like the coach of the basketball team, and the executors are the players of the basketball team. So we're going to be kind of using more analogies here. I need to update these slides so they actually have like basketball players in them, but it'll make a lot more sense as we kind of go through this. So remember, we have the play, the coach, and the players. And those are going to be the 3 things that we have, but they're called the plan, the driver, and the executors. Okay, so the plan. You can think of this as the play. This is like the coach will tell the players what play to do. And this is going to happen like where the play can be described in whatever way you want to do it, whether usually it's going to be Python, Scala, or SQL, or R if you want to be a weirdo. And then the plan is evaluated lazily. What that means is the plan doesn't actually run until, I like to say, like a player takes a shot, which means like they either like try to write data out somewhere, or they try to collect data somewhere. So that's what taking a shot means, like writing output or collecting data. And the collect, what that means is like essentially they are taking information from the play and bringing it back to the coach to have the coach tell them what to do next. And that's going to be the main things around the plan of how Spark works. So this is going to be like your data frame code. This is going to be your Spark SQL. This is going to be your data set API code. And that's essentially what we're going to be working with here. So that is kind of the plan of how Spark works. Okay, so you have the driver, which is like the coach. You can think of like the coach reads the plan. So the coach like tries to figure out what plan to run and what play to make. And Spark only like so you the driver can have a couple settings that it can have in it, but there's like probably 10 different driver settings for Spark that you can set. Really, there's only 2 that you need to care about here. Spark.driver.memory, which is going to be the amount of memory that the driver has to process the job. I think this defaults to like 2 gigabytes. It can go all the way up to 16. Generally speaking, the only times that you need to bump it up is like if you have a crazy complicated job that has like so many steps and plans, you might need to bump it up in that case. Or if you do collect, where like the data that the job is processing changes the plan of the job, which mostly is bad practice. You don't, generally speaking, want to do that. There is some edge cases where you want to do that, but like for the most part, you don't want to do that. But those are going to be the only 2 cases when you really need to bump this setting up from 2 gigs to whatever other number you want to bump it to. The only other one that you might want to also change is memory overhead. So this is where the driver needs memory to process the plan, And if for some reason you have a very complicated plan, you might need more overhead memory, because the JVM might take up more memory in those cases. So you might want to crank this to a different number, which is so that your non-heap memory is the memory that Java needs to run, not like the memory for the plan or the memory for the collect calls or the memory for anything like that. It's none of that. It's just the memory that Java needs to run. And the only time that needs to be bumped up is if you have a very complex job. Every other driver setting you shouldn't touch, at least in my experience. I've spent many years. I've been playing around with Spark for 7 years, and I've played with all of these settings just to see, played a lot of what if and science and experimentation games with a lot of these settings, and these are the only two that I've seen that have any sort of substantial impact on the performance of the job. All right, so that's the driver. So keeping in mind, the driver determines a few things for you. So the driver determines when the job should actually execute. So that's when it finds an output or a collect call. It will find those to tell the players to start running the play. It will also figure out how to join the data sets, which can be very, very important. Because depending on what type of join Spark decides to use, that can mean that your job is 10 times less performant or 10 times more performant. And it also determines how much parallelism is needed in each step. So for example, if say you have two data sets you're reading in, and then you join those two data sets, and neither data set is small. You have two big data sets you're reading in. So generally speaking, the initial parallelism for those steps is how many files those data sets are written to. And then when you join, then you get into the parallelism step, which we're going to talk about here in a second. And that is how much parallelism happens after a join or something like that. And so those are the three things that the driver really is all about. And if you can get the driver to do these things the right way, then you can have way more efficient Spark jobs. So let's talk a little bit about the executors. Executors here are going to be what actually do the work. These are the Michael Jordans and the Kobe Bryants and the LeBron Jameses of the Spark framework. And they actually do the work. They're the ones who actually take in the data and then transform the data and filter and aggregate and whatever other operations you want to do on the data. So in this case, there's really only about three settings here that you want to touch in terms of executor settings. In this case, you have Spark executor memory. This has the same constraints as driver memory. So it defaults to 1 or 2 gigs, and then it can go all the way up to 16 gigs. I've seen bad practice with this, actually, where there's if a job OOMs, right, out of memory exception, one of the things that can happen here is people will update this to 16 gigs and then just forget about it. And they're whatever, it's fine, even though it makes it so the job, it runs way more expensively. Generally speaking, the way I like to think of how to set your executor memory is you want to try running it at a couple different memory levels, running it at 2, 4, 6, 8, something like that. And then one of them is going to run all the time. And once you have the one that runs all the time for a couple days, that's the smallest number that runs all the time for a couple days is the kind of way that I like to figure out the right number here. Because one of the things that's tricky about this is you don't want to have too much padding, because if you have too much padding, you're just wasting all this memory. But you also don't want to have too little padding, because then the chance of out of memory is annoying. And when things break, engineering time is one of the most expensive things for a company. Data engineering time, your actual time, is more expensive than the cloud costs of a little bit extra memory usage. A little bit of wasted memory usage is going to be worth the trade-off of your actual time on the job. So that's the way I like to think about it. But I also am against just setting it to 16 gigs and then just setting all jobs to 16 gigs and calling it a day. because I think that that's terrible. Then you have executor cores. So generally speaking, an executor can take 4 tasks at once. You can go up higher to 6. I would say you can go all the way up to 6 if you want. And then this makes it so that you can get more parallelism per executor. But if you have more than 6, the thing that happens is you get a different bottleneck, right? The bottleneck in that case is the executor disk and the throughput between like when tasks finish. And so you don't want to crank this up higher than 6 because you end up bottlenecking yourself by the throughput of too many tasks running at the same time. And so generally speaking, you want it to be 4. I don't generally touch this setting. I've seen people touch this setting and see some results, but generally speaking, I don't touch this. But maybe crank it to 5 or 6 if you want to get a little bit more parallelism, make your job a little bit faster. But more than that, like, it's a trade-off, right? You can't just crank this up to like 1,000 or something like that, because obviously your executor doesn't have 1,000 cores to begin with. But maybe you can leverage a couple more. You want to be careful there too, because like if you crank it up to 6, then you have 6 tasks on one executor, and it also makes it more likely to OOM, because depending on the memory footprint of each of those tasks, if they're all running at the same time, then it's more likely to OOM, because the probability that you get you have 6 tasks that are skewed a little bit more is higher than if you have 4 tasks that are skewed. So that's just another thing to think about. And then you have the memory overhead, just like you have with the driver. In this case, you really want to maybe bump this number up if you have jobs that have a lot of UDFs, especially like if you're using PySpark. PySpark UDFs are terrible. Just UDFs, a lot of complexity, a lot of joins and unions and all sorts of, like, if the plan is crazy and like you need, your JVM might need a little bit more of the memory footprint. The thing about this is that I like about the memory overhead is that you can increase the memory overhead without increasing the memory itself. You can make the job more reliable at no additional cost. So that's the thing I like about these overhead settings, is that they can actually make a difference. So definitely try them out, especially if you have a job that's a little bit unreliable. That's a good kind of setting that you might want to fiddle with. So remember, we're going back to the analogy real quick. So we have the plan, which is the play that the players make. You have the driver, which is like the coach, and you have the executors that are the players that actually run the play. All right, this is a very, very important slide in Spark here. So generally speaking, you get, there's essentially 3 types of joins in Spark. You have shuffle, sort, merge join, broadcast, hash join, and bucket join. These are going to be your 3 joins that are important. Shuffle, sort, merge join is going to be the least performant. Broadcast, hash join, and bucket join are going to be a little bit more performant. But shuffle, sort, merge join is also useful because it's the most versatile, because it works pretty much no matter what. Whereas broadcast and bucket join work under very specific circumstances. So broadcast hash join works when one side of the join is small. And it actually doesn't have to be the left side of the join. It's just one side of the join needs to be small. And then it works pretty well, because in that case, instead of shuffling the join, it just ships the whole data set to the executor, and you don't have to shuffle at all. And it works great for small-ish amounts of data. Like, I've been able to broadcast up to like 8 to 10 gigs. If you try to broadcast more than that, you're going to bump into problems with executor memory at some point. So that's a thing to think about when you're determining which joins to pick. Bucket joins are going to be where if you want to do a join without shuffle, you can do that with a bucket join. I have some diagrams in some future slides that will kind of explain more about like how this works. But so you have shuffle, sort, merge join, broadcast, hash join, and bucket join. And being able, like in Spark, you use .explain and it's going to bring up these words. So you need to know what each one of these words means if you want to be able to optimize your Spark jobs. Generally speaking, you want to minimize the amount of times you use shuffle, sort, merge, join. That is a very hard word to say. Too many S's. But broadcast and bucket joins are going to be your best friends in a lot of cases. So let's just talk about shuffle real quick, because I think shuffle is an important part of this puzzle. So shuffle is going to be like the least scalable part of Spark. That's the thing. And the more you shuffle, and as scale goes up, the usage of shuffle gets more and more painful. And it gets to a point when once you're over 20 or 30 terabytes, if you're trying to process more than 20 or 30 terabytes a day, then shuffle just goes out the window and you can't do it. You got to solve the problem in a different way. So anyways, you can think of imagine you had a job you have a table that you're reading in, and it has 4 files. And what we're going to do is we're going to do a map operation first. Maybe we add a column or we filter it down. So map operations here are going to be where, or you add a column, you add a new column to it. You do select star, comma, and then you add another column. Or dot with column if you're using the data frame API. And then you add columns. And then and the thing about that is it's infinitely scalable for the most part. It's scalable to the number of files, and you don't have to do anything, and you don't have to shuffle. But then what happens is imagine then you need a group by. So in this case, we're saying that there's 3 partitions in Spark. The default is actually 200, but I didn't want to build a diagram with 200 squares. So this is just kind of a simplified view of this. But what ends up happening is imagine you have you're grouping on user ID in this example here, and then everything in file 1, all the user IDs, if they you divide the user ID by 3, and then you look at the remainder. If the remainder is 0, it goes to partition 1. If the remainder is 1, it goes to partition 2. If the remainder is 2, it goes to partition 3. And same thing happens for file 2, file 3, and file 4. And so all the data from file 4 will be kind of in files, will be in partition 1, partition 2, and partition 3, depending on where they're at. So this is how shuffle works, and this is how, if you imagine on both sides, so this is just a group by operation in this case, but if imagine instead you were doing a join where files 1 and 2 were part of one table and files 3 and 4 were part of another table, and then you want to join them together, then you can do that the same way, because then they'll shuffle, and then all the data, all the user IDs that are divisible by 3 go here, right? And then you get all the right data in each partition, and then you can do the comparisons, and then you can actually do the join on the data with the relevant data there. So that's essentially how this is the default case. This is going to be that shuffle, sort, merge, join. That's going to be how that works, right? So the difference here for if you're working with a broadcast join is instead you don't even need to shuffle, because what you can do is the broadcast join can just, files 3 and 4 are small enough that you can just ship all of the data to each of these executors, to file 1 and file 2, and then they can do all the comparison and all that stuff in this spot, so they don't have to do any shuffling at all. And that can be a very powerful way to go about things. Anyways, we're gonna go back to this slide in a second because I want to talk more about buckets, but let's go a little bit deeper into this presentation. So shuffle partitions and parallelism are linked. They are actually the same thing. It's kind of weird. Spark is so weird because it has these 2 settings, as spark.sql.shuffle.partitions and spark.default.parallelism, and they are, for the most part, the exact same thing. Unless there is one tiny exception, and that's if you are using the RDD API directly, then spark.default.parallelism is the setting to use there. But if you're using anything else, data frame, Spark SQL, dataset API, any higher level API, which you should be doing, don't use the RDD API. Like you should almost never, ever be using the RDD API. There might be a small, tiny edge case where you should, but like 99% of the time, you should not use the RDD API. You should be using the higher level APIs. That's guidance from Databricks and from Spark as well. So these shuffle partitions are linked with parallelism. This is essentially, if you go back to this slide here, this is the number of partitions that you get after you do a join or a group by. So let's talk a little bit about shuffle. So is shuffle good or bad? I think so far in this presentation, you might be considering shuffle is kind of bad. Shuffle is probably not what we want. And I don't agree with that. I think that shuffle is actually pretty decent. That like you should probably use shuffle in most cases, especially if the volume is not really high. In this case, I'm saying volume being greater than 10 terabytes. Even 1 terabyte shuffling is pretty decent. And so I have an example here I want to go over real quick, and I'll send you guys the link to this. There's some writing online about it as well. But so one of the pipelines I worked on in Spark, this is the biggest pipeline I ever worked on in my entire career, was it processed about 100 terabytes an hour in Spark, and we had to do a join. And so what we needed to do was every row in this data set was a network request. It was every network request that Netflix received, and we wanted to join that data set with a data set that mapped that network request's IP to a microservice app. Like, because Netflix has thousands of microservices inside of its architecture, and we wanted to figure out which IP, where was this request coming and where was it going, just so we could see like which app is talking to which app. That was the whole idea behind this pipeline. And so one of the things that was nice about that was we were actually able to ship all that lookup table, that IP lookup table. We were able to get it down to like, several gigabytes, and we were able to broadcast join it, and it worked. Then a new requirement showed up for that pipeline, and that was because Netflix wanted to upgrade all of their services to IPv6 instead of IPv4. Then at that point, we were trying to ship things over in IPv6. And I don't know if y'all know, but IPv6 is, I think, 100 or 200 or it's like 100 or 1,000 or 10,000 times more IP addresses than IPv4. So it goes from like billions to like quintillions or something like that. Like it's a very, very much bigger search space. So when we tried to move over, then it no longer was a broadcast join, and then it had to be a shuffle join, and it didn't work. Couldn't do it. Like that was just literally not possible. Because it was too much data, and there was no way that this join was going to work. And so that was a very painful thing to realize, and we realized that, okay, shuffle actually can bring some pipelines to its knees. I found that there was a lot of some other cases for me at Facebook when I was doing some like feature generation stuff for notifications, where we had to join two tables at the notification level. So you had like notification, join notification, and then it was like 10 terabytes on one side and 50 terabytes on the other side, and we tried to join them together. And like they did that for a while, and like that was what they did, but it took up like 30% of all of the compute that we had for all of notifications, this like one whale behemoth of a pipeline. And so you want to be careful in some of those cases. What do you do like in those cases? So I think depending on the use case, you can kind of do things in separate ways. I want to talk about how I solved both of those problems. So let's talk about the notification one first. So for the notification data sets that we're joining at that very at that cardinality down there, like instead of doing a shuffle sort merge join, we bucketed the tables, and we bucketed them on user ID. So what we did was we put each side of the both the left and right side of the join into 1,024 buckets. And then what we did with that was then when you do the join, you can do the join without shuffle, because if you go back to forward, because in that case when everything's bucketed, you don't the files already they already have the guarantee that the data, all the data that you're looking for based on that ID already exists in that file. You already have that guarantee because it's bucketed, and that's what the files, essentially how you write the files is based on the user ID. It's you modulo the user ID, and then you write the buckets out. And then when you do the join, you just match up the buckets. So in this case, imagine you had two tables and they both had two buckets, and then and they were both bucketed on user ID. Then instead of having to map like file 1 to partition 1, 2, and 3, and file 2 to 1, 2, and 3, what you could do is you would just line up file 1 and file 3, because file 3 is the first bucket of the second table, and file 1 is the first bucket of the first table. And you essentially just line up the buckets, and then everything works, and then you don't have to shuffle at all. And you get a massive, massive, massive performance gain if you do that with buckets. And interestingly enough, you can actually, even if the two tables don't have the same number of buckets, you can still do a bucket join, assuming that they are multiples of each other. So imagine in this case, instead, we had one table had one bucket and the other table had two buckets, or you can think of like 2 and 4 or 4 and 8. Well, in that case, like files 1 and 2 would have all of the data in files 3. Because like it would be, all of it would line up because they're multiples of each other. So the big lesson here is that when you're bucketing your tables, always bucket your tables on powers of 2. Always use powers of 2. Don't be weird and be like, I want 7 buckets or like 13 buckets or something like that, because then like the only way that you can get a bucket join is if the other side also has 13 buckets, and that might not be the case. Like and so one of the, I think, bigger questions here is like, how do you pick the number of buckets? Well, in some of these cases, it's based on the volume of the data, right? And then you want to kind of divide it where it's like, okay, I know for like at Facebook, like we had 10 terabytes. And so you're like, okay, 1,024 buckets. We were like shooting for like, in that case, I think like 10 gigs a bucket or something like that. That was kind of the idea. But like, there's kind of a rule of thumb there where like, because if you have too many buckets on data that's too small, then you have that same problem where there might not be any data in one of the buckets because of the modulo problem, where like, if say you have like 1,000 rows and you're like, okay, I'm going to bucket this into 1,024 buckets, then you're guaranteed in that case to have 24 empty buckets by the, I don't know if y'all know that, the pigeonhole principle in combinatorics, but you're guaranteed to not have enough data in one of the buckets. And if you have an empty file, that can mess up with a lot of these systems, and it doesn't trigger the bucket join the right way. So like that's where you want to make sure that like you aren't putting too many buckets on tables that are small. That's just kind of an aside. So that's how I solved the problem at Facebook. But what about the problem at Netflix? That problem was different. So one of the things about that problem was bucketing the 100 terabytes an hour was going to be very expensive anyways, because you have to shuffle. That's the only way that you can do it, is you got to shuffle that 100 terabytes an hour. So in that case, we actually solved the problem upstream, where what we did was we got everyone to log their app when they received a network request. So we went and talked to all the microservice owners, and we were like, just log your app, please. And that's how you solve the problem. So you just put the app in the data. So then you don't do the join just goes away. And that was how we solved that problem. Obviously, that solution was also a massive, massive, massive pain, because you have to talk to like hundreds and hundreds of people. But that's how we solved that problem. And so there's a bunch of different ways to solve these problems, but and know that like what I just said is that like you might not want to use a Spark optimization technique to solve your problem. Just like what I said right there, right? Where it's like, maybe it's a logging problem. Maybe you're trying to solve this problem with a hammer because you're good at Spark. And so every problem seems like, every nail seems like you need a hammer to hammer it down. And that's not always the case. Like sometimes you need to solve the problem upstream, and you need to work and have people, like other people give you the data the right way, as opposed to trying to bring it all in, especially as you get to bigger and bigger scales. That's usually how you solve the problem. We're going to talk a little bit about minimizing downstreams. I talked a bit about this already, but bucket the data if multiple joins or aggregations are happening downstream. Bucketing is great, but like if you're bucketing and you're only doing one join, then usually that's a waste, because like because you have to pay the shuffle cost already to bucket. That's the cost, because you have to, in order to write to a bucketed table, you have to put that in there. You have to already have that in there. So and then if you're only doing one join with it, then like, why are you doing that? Like, you really only get benefits from bucketing is if you are doing multiple joins with these tables, because then that's when you're going to really see the big benefit. So that's a good thing. Remember, the one thing about bucket joins that I want to talk about is Presto can be weird with bucketed tables, because especially if you have tables that have a small number of buckets, maybe it's like 8 or 16 or something like that, then when you query stuff with Presto, like the query might be slower because the initial parallelism will always be 16, and like maybe Presto wanted more, and like when it's a non-bucketed table, it can split the files up and it can like handle it better. But generally speaking, I like buckets. Buckets are good. And the last thing I wanted to say is that if you're playing around with buckets, always use powers of 2, 2, 4, 8, 16, 32, 64, 128, 256, 512, 1024, just powers of 2. Always use powers of 2. So minimizing shuffle is, I would say, one of the most important things that I did in my career that has helped me move up the ladder, because you can save a lot of money, especially at big scales with this. Okay. Let's talk about shuffle and skew. Skew is another one that I noticed that was also, I had to deal, like, skew's gotten so much better though. Oh man, like y'all are lucky. I feel like this is one of those, like, back in my day, like things were difficult, right? So skew happens when you partition your data, right? Where you have that modulus thing, right? Where you divide by 200 and then you split up all the data. And the problem happens, right, is where one of those 200 partitions has way more data than the other partitions. Like, what you can imagine in this case is, like, imagine if, like, Beyonce and Justin Bieber and, like, I don't know, like, The Rock, they all, somehow miraculously, all of their user IDs are divisible by 200. And then what happens is, every single time all of their notifications go to the same executor, and then it's like them and then like a bunch of random people, and then like, but just those 3 users are going to have dramatically more data than everybody else because they're famous. And so they're going to skew. That one executor is just going to be given, like, I don't know, 10 or 100 or 1,000 times more data than the other ones. And that can be a showstopper, actually. I mean, that's taken so many pipelines down. And another symptom that can happen here is your jobs will get to 99% and then fail. That is probably the most infuriating thing about data engineering in my mind, like, at least from a technical perspective, is like, skew is like such an asshole, because it's like, okay, we're gonna almost run. We're gonna let your job run for 2 hours and then fail. And then you're like, why did it fail? Like, come on. Right? And so that is why I don't like skew. But things have gotten a lot better with skew, and we're going to talk a little bit more about how to solve these problems. So how to tell if your data is skewed, right? I was talking about this. The most common symptom is your job is going to get to 99%, and it's going to take 1,000,000 years, way longer than you expect the job to take, and then it will just fail. And it's sad, because you're like, wow, why did it fail? Another more scientific way is you can actually like do a box and whiskers plot and actually like map it out and do it like a data sciencey way. I've literally never done that, but if you want to do that, you can do that and like have more confidence that your data is skewed. I almost always just like build my pipeline and then get mad when it fails at 99% and just like kind of do it the hard way and not the scientific way. But that's how you want to know. Tell if your data is skewed. Let's talk about how you can actually solve this problem. Okay, so the most effective way to solve this problem is, but it's only available in Spark 3, and we're going to talk about it real quick, is you need to set this spark.sql.adaptive.enabled and just set it to true, and that will solve your problem. Done. Like, you don't have to do anything else. It's amazing. Like, I love this setting, because then you don't have to do all, like, well, I'm going to talk about one of the ways that you can do it if you don't have Spark 3 and you have a skewed group by. This doesn't work with a skewed join, but it works with a skewed group by, where what you do is you essentially you add a column, which is just like a random number, because then what that does is it will break up the skew, because then some of the skew will go to one executor, some will go to another executor, and then you essentially do two aggregations where you aggregate once where you group by the random number, and then and that gives you like a partial aggregation, and then all the skew data will be small at that point because it will all be back down to like whatever your group by grain is. And then you aggregate again, and you just remove the random number and sum everything up again. So you do two sums, and that will give you the same thing as you would get otherwise. So you want to be careful using this. I don't know if y'all remember from a previous presentation, I talked about additive and non-additive dimensions. And this is a great example of where additive and non-additive dimensions can mess you up, because if you sum something twice like this, they might not actually add up to the same number. But it depends on or add up to the correct number, and it depends on the dimensions. But generally speaking, most dimensions are additive. I think like about 80-90% of dimensions are additive, and so you can use this and it works great. But make sure that you are aware of that before you use something like this. But generally, just use spark.sql.adaptive.enabled. Obviously, don't just set this to true all the time, like just in case, because it makes the job more expensive to run, because Spark has to compute all these like extra statistics about the job while it's running, and that you don't get those for free. And it makes the job slower, but it makes the job more resilient to skew. And so that's why it's great. And hopefully y'all are just on Spark 3, so you don't have to do this like random salting hack. I want to talk about one more way to deal with skew in joins. And this is what I did at Facebook was if you have a join, the problem is like you can't have this like random number thing. It doesn't work the same way. And so what I did in that case was I identified the outliers and like just filtered them out. And then just was like, okay, we don't need these IDs. And then I was like, Beyonce can just wait. They can wait and have data tomorrow. And sometimes that is an acceptable way to deal with skew, is you filter out the outliers. Or what you do is you partition your downstream table, where you have one side of the pipeline that processes everybody else, and then you have the other side of the pipeline that processes the outliers. And in that case, you can usually that can usually work pretty well. So that's another way that you can kind of manage stuff. But those are essentially the main ways to deal with skew. Okay, let's talk a little bit about the ways Spark is kind of ran. Y'all know we were going to use Spark on Databricks, and then it kind of fell through. But Spark on Databricks and Spark unmanaged Spark kind of have different ways that you want to run and test your job. So generally speaking, should you use like a PySpark notebook when you're running your job? This is something I remember back in 2018 when I was working at Netflix, and then they got this working because Netflix kind of pioneered the idea of running notebooks in production. And I was like, I still don't like it. I still don't like it at all. I don't like the idea of running notebooks in production because it's like unchecked mutations. You're not using Git. Like there's a lot of problems with it. But Databricks, like they all are about it. Like that's what the whole UI is all about. They really want you to use notebooks, right? Databricks are all about it. So, but in big tech, you should probably only use notebooks for proof of concept, and then check your Spark code into like a Git repo. And then you're going to use this thing called Spark Submit from the CLI in big tech, whereas like you can just run the notebook in Databricks. So that's kind of like the difference between Spark on Databricks and regular Spark, like thinking about like kind of best practices. I personally like unmanaged Spark using Git and Spark Submit for my jobs. I'm kind of anti-notebook because I feel like notebooks, they don't invite unit tests, and they don't invite integration tests, and they don't invite good engineering best practices. But they invite less technical people. Like they invite people who don't have all of the technical things and allow them to actually leverage Spark. So that's where they're useful, is they actually allow people to use Spark and they don't have to be so technical. So that's why they have adoption. But as data engineers, I generally think that it's like not the right way to go. So Anyways, that's Spark on Databricks versus regular Spark. I just like to call that out. So remember I was talking about all those different types of joins. One of the big things that you want to do, and we're going to check this out a little bit today in class, is we're going to look at this .explain. So you can look at Spark will actually tell you everything that you want to know about it if you use the explain in your data frames. And that's going to give you a lot more insight into actually how Spark is running underneath the hood. Definitely check it out. It's very similar to like explain in SQL. You could actually, I'm pretty sure you can use Spark in Spark SQL like the same way, where you put like explain at the front. Okay, another thing just to talk about is like where can Spark read data from? I'm sure y'all know, just like the answer here is everywhere for the most part, like from the Lake, Delta Lake, Apache Iceberg, Hive Metastore, Postgres, Oracle, REST API calls. You want to be careful. I think that's one of the things here I want to talk about real quick is like when you make a REST API call, it's almost always done in the driver. And remember your driver memory settings. So like if you are making a REST API call and the response, or you're making many API calls and the responses are big, then you want to be careful how you're processing that data in Spark, because it is a lot more prone to running out of memory. So and in those cases, like a lot of times you might want to like parallelize them. So like what you can do is like you get a list of URLs and then you do spark.parallelize, and then you essentially make the API calls in the executor. It's a trade-off though, because the nastiness of that is then you essentially hammer the API in parallel, and that can be a problem, and that's like a separate problem versus like managing all the memory in the driver. And those are two separate problems that I find. So for me, I generally find APIs to like not be very like REST APIs. I don't find them to be very Spark friendly unless it's like if it's like one call, then usually it's like whatever. But if you're making a lot of calls, Spark might not be the right way to do it. So that's a thing to think about. Like a lot of times, like the way that Spark likes to do it is instead of calling and hitting the REST API, they like to read directly from like the Postgres database or the inner guts. They like to essentially bypass the API and read directly from the data tables. And Spark's going to have a way nicer time doing that than reading from an API. So definitely know that whenever you're doing your integrations, that's probably going to be the smoother integration, is like where you go up a layer and you read from the data tables as opposed to trying to read from the API. And obviously flat files. We're going to be using flat files today in the lab. So that's pretty much it for how Spark can read data. So Spark output data sets. Almost all data sets in Spark, when you output them, should be partitioned on date. This date should be the execution date of the pipeline, which is like, if y'all use Airflow, there's like, it's like curly brace, DS, curly brace. Like it's like that is like the param. It's like the date that you want to backfill or the date that you want to run the pipeline for. That date should be passed to Spark, and then Spark can, write the right data accordingly. DS partitioning is very powerful. Definitely look that up if you're not familiar with that, because if you're not partitioning on date, like your tables are going to get way too big and way too bulky. So good thing to remember. Congrats on making it to the end of the Spark Basics lecture. If you're taking this class for credit, make sure to switch over to the other page so that you can do the lab and get credit there as well. Welcome to the Basics and Spark Advanced setup example. So what we're going to be wanting to be doing here first is make sure you have Docker desktop running and installed. That's going to be the big thing. And then you want to go to the Data Engineer Handbook, and you go Bootcamp, Materials, Spark Fundamentals. And then in here, you'll see there's a Spark Fundamentals and Advanced Spark Setup. So there's two options here. You can either run makeup or Docker compose up. So in here, I'm just going to show with Docker compose up. Now this is setting up and running all of the Docker stuff that it needs to download and install and do all of the stuff to like set up Docker. You'll see this needs to set up 4 containers. We need one for Iceberg, we need one for MinIO, we need one for MC, and we need one for Spark Iceberg. Those are going to be the 3 big things that are going to be part of this, right? And then ultimately we are going to be accessing this from localhost 8888. That will be where this is going. Make sure you have Docker set up, otherwise this is not going to work, right? And this is going to take a little bit of time because these images are really big, right? So we're just going to have to vibe here for just a little bit while this is installing, and then we'll go from there. It should be a pretty exciting time here as we get to the actual setup here, because I know y'all are really excited to get ready to test out some Spark stuff. Should be pretty great. So I think if we go here, is it set up? Okay, there we go. So that actually set up. Then we can go into notebooks and we can go here, right? And then this should run. So you'll see we have our data pulled in here. This is all of the data that we have. And so if you can get this up and running, you're good to go for the lab. One of the things I want y'all to try is just like running this first cell, and you should get, this should actually show you some data here. It should give you back a good data set that will show you pretty much what you would want to see here around like URL, your browser family, device family, host, all that kind of stuff. So one of the things that this is probably pretty straightforward so far, we're just reading in a table. It's reading in a CSV file that is the one CSV file that's in the repo. So, and then we're adding one column here, which is the event date. And the reason why we're adding the event date column is because we want to use that later on in Iceberg. But I actually learned that like you don't even need this column for Iceberg. Like Iceberg is actually really smart. But so I just want to kind of go over each one of these lines real quick, because some of y'all might not have a ton of experience with this line. Actually, we don't need it. So Spark is managed by this thing called the Spark session. So you want to build a Spark session. So that's what Spark session.builder does. And then usually you create some sort of app name. We call it Jupyter here, which is your Jupyter notebook. And then you do .get or create. One of the things that you might notice here about this syntax is that it's actually not Pythonic. Because if this was like a Pythonic way, right, this would be get or create. Right? It'd be like that. And one of the reasons why it's not that, and it's actually this, it's camel case and not snake case, is because Spark is a JVM library. And so even when you're using Python, PySpark, you're going to still, a lot of the libraries and functions and stuff that you're going to call are going to be JVM. Same like with this with column, it's with column, not with column like that, right? So most of the style, like this is where like PySpark can be a little bit funky, because like you actually do use Java styling, but you have Python code. And the main reason for that is that PySpark, all it does is it wraps the Python, wraps the Spark libraries in Python, so that then you can just use Python to do stuff, right? So one of the things I wanted to show real quick here, though, is you see there's .show. I wanted to show .collect. This line, this might actually out of memory. Let's try it. Oh yeah, I forget. Oh yeah, Python is so annoying. You have to put the backslashes. Okay, so you see how now we're getting a stage. It actually gave us a stage, and that actually gave us, we're actually like running Spark there. Okay, so there we go. Wow. It's because there's not tons and tons of data. So generally speaking, if this was a very big data set, like if it was actual big data, I think there's like 500,000 rows here. But like that is going to be the idea, right? Is that you can also kind of out of memory and crash Spark by calling this df.collect, right? So I kind of want to show that just because I think it's important to illustrate, right? Because you can do like a join here, or like here, let's do it this way. We're going to say .join df, and then in this case, what we're going to say is df, or we're going to say, can we just say lit? I think we say lit1 equals lit1. So like we're essentially going to just like blow up the data set here by like doing essentially like every row matching with every other row. So this is going to make it like a lot more data. Like, and so I wanted to show you how this is going to probably crash the data set, right? Okay, there we go. So now we're saying, okay, perfect. So you see here how what we're doing here is we have this Java heap space problem where it's like out of memory because we tried to bring too much data back, right? So what we could do, right, is if we say instead of collect, say we do like dot take 5. Now this should actually run. Like I'm pretty sure this will run. Okay, hold up. 1 second. Let me see, because if I try to run collect here again, it might have just died. Okay, so I straight up killed the kernel here. So we gotta like stop him and the kernel. We gotta restart the kernel here because I straight up killed the kernel because we did a nice little OOM there, right? So which is a common thing, right? So this is a great example. My whole point here is that this is a bad practice that I've seen many times in many Spark jobs is if you call .collect like this, make sure that it's filtered down. You don't ever want to pull in the entire data set into the driver, ever. It's just not something, that's not something that we do. So I'm pretty sure though if we do .take 5, this should still run. See how it's actually like thinking about it this time and it's not just like barfing because I'm not trying to bring back because that's a 400K times 400K. I think that's like 1.6 bill. So this is still going to take a little bit because we're doing this like crazy cross join, right? But the thing is this is now like whenever you're bringing data back to the driver, it should always be limited or another way to think about it is like this should be aggregated or limited or anything like that. There should be something that happens that is the kernel like even running? It says the kernel is idle. Did I like straight up kill the kernel right now? Okay. Let me try and run this again because this should be okay. There we go. Now it's alive now. I just had to refresh. So this is going to be running now, and this will actually. I'm pretty sure this is not going to OOM because see, boom, didn't OOM. Even though we did a crazy cross join here, right? So be aware of that bad practice because I've seen that bad practice many times in my career, right? And so you want to like filter this down, like either like so generally speaking, the way I think about it is like you want to be using take and show and not really using collect. Collect is the only time you want to use collect is if you know for sure that the data set that you have here is like aggregated down and you can use that as your data set. So that's something that I just am cautioning you about because I think it's very important and just kind of showing you how like, hey, you can kill Spark. You see how I killed Spark there? It's great. I love killing Spark because it's like it's a fun thing to troubleshoot. So anyways, I'm going to get rid of this cross join line because it's going to make everything really slow later down. But let's talk about some more lines of code here that are going to be different and kind of things here that like I want to show you about how these lines work and how we're going to split things up and we're going to figure things out. But here's the idea behind what this is going to do and like how this works, right? So you'll see df.repartition. So what this is going to do is however many partitions we had before, we're now going to have 10 partitions and we're going to split it up based on event date. That's going to be the column that we're looking at, and that's how we're going to split data up. And then we have sort within partitions. So I want to show you the difference between a couple different things here. So we have, so you see how we have this one? I want to copy this line here, and I want to, we're going to create another line here. But you'll see you can also just do .sort, and this is going to be, we're going to call this sorted to, and then we're going to say sorted to.show. So, because these two are actually the same in some regard, but they're also very different. So let's see if this actually works. Okay, so you'll see that one of the things you'll notice between these two is they actually pull different data. Like you'll see that in this case, we have data all the way back to 2019, the 12th, and then here we have data back to the 14th, right? So it's like, why is that the case? Like, what is the difference between these two, right? So that's one of the things that I think is important to talk about because these both are different and they actually are very different at scale. So I want to just really emphasize this with y'all, because what I'm about to show you is another very powerful thing, but you want to make sure that you understand these APIs clearly to understand why these are different at scale. So let's talk about what so it says sort within partitions, and this is sort. So if you do sort within partitions, it will just it will take every, like the 10 partitions that you have, it will look at all the data in those partitions and sort all of them kind of locally within that partition. And in this case, we're going to sort on event date, host, and browser family. And the difference between that and .sort is, you'll see here, with .sort, we actually get data all the way back to, this literally does what's called a global sort. So this is sorting data as far back as you can go. And it doesn't just sort the data within the partitions. It does a global sort of all the data. And so that global sort like that is actually very slow. So these two, because the data isn't very big, these two, like in this data set, are going to be about the same. I think we can we do, I think we can do this. I think we can put a .explain in here, and I think this will give us what we're looking for, because we want to check out .explain. Okay, so, oh, it's because .show doesn't exist, so we'll just get rid of .show. You just got to do just .explain. Okay, so what we want to do here is let's look at the difference between these two plans, just so we can kind of understand how they are different, because they are significantly different here. And I hope that y'all can understand what's going on here. And because this is where using .explain can make a very big difference in understanding what is happening with like the difference between this sort and this sort. So in this case, okay, like we see, so the way these explain plans work is you go to the most indented thing first, and this is going to be the first step, which is we read a CSV file. Makes sense, right? And then we select our columns, right? Which is going to be, that's what project means. Project and select are the same thing, right? And then we do an exchange. So this exchange in this case is going to be, that's this repartition line, right? That's what that's going to do, exchange. And then we have our sort here, and that's going to be the next line. And there's this, you'll see there's a difference here, this false and this true. And that's going to be based on whether or not they are doing a global sort or not. And so that's going to be the next kind of line. And then you have, after that, you have the project, right? And then this is the final select, where you're selecting out the columns again. So you see that like we ended up selecting these same columns from here and here. Those are the same like list of columns. So how is that different from this one? And you'll see that this one has one more line in it though, because you see here's the hash partitioning where we repartition into 10, but then you'll see this you see this exchange here, this exchange range partitioning. You see this guy. You see how this line is not in this one? See this range partitioning here? This is the line that is going to be painful at scale. This line is going to be very, very painful at scale. So that's how you can tell when you look at these partitioning plans. Like, so what this is saying is, okay, we're going to shuffle once here, and then we're going to shuffle again. That's what this, every time you see the word exchange in a query plan, think exchange means shuffle. Shuffle and exchange. Those are like the same sort of words. That's exactly like, they're synonyms when you're looking at the plan and when you are running the job. So you'll see when you use the .sort here, you get freaking, it's nasty. It's real nasty because you get this double shuffle, right? But if you use sort within partitions, you only get one. Like you just have one. But this, like, honestly, if you remove that repartition, right? Let's run this again, and you'll see now in this case, right? There's just we have the file scan, we have the project, and we have the sort. No shuffle. Right? Because I just deleted the repartition. But like in this case, even without this repartition, so if we just have .sort here, and we run, so we get rid of both repartitions, you'll see we still are going to have this exchange range here. And this is like, especially if you have more than like, I don't know, like 20 gigs of data, this line is going to be very slow. Because the thing is like when you do a global sort, you have to pass all the data through one executor, because that's the only way you can guarantee that the data is globally sorted. It's the only way. So my main point with this is at scale, you want to use sort within partitions and not sort. You should almost never use dot sort. Sort is like, I don't like dot sort. I think it's whack. Like I don't like, you should not think about using dot sort. So this concept right here can make your pipeline way more efficient as well, because knowing how to sort stuff when you write it out makes a big difference. And we're going to talk about that in here in just a second. Okay, great. Now, what I want to talk about now, to shift gears here a little bit, is around, we're going to talk a little bit about Parquet, talk a little bit about Iceberg. Might go a little bit over today, but so we talked about sorting, super important. I want to run this sorted line again, because we're going to be using this sorted line. So what I want y'all to do is also try to run these other kind of bootcamp SQL lines, because they're going to be important here. So, okay, so let's go to this line where we're creating this Iceberg table. So you'll see in here, we can you can partition your data however you want in Iceberg. And it's cool because like you can actually, like in this case, you can say years, like, or you can say days. You can even say hours here, or years or days, right? And then that will actually look at that timestamp or date field, and it will just split it there. But you can also just do event date. I'm actually gonna do event date. It doesn't matter. You can keep it as years. It doesn't matter that much because we're gonna be running all the data together. So then we have that, and then I'm also gonna put the partitioned here, partitioned by event date. In this one, I'm gonna run this. Oh, there's a semicolon. So hopefully y'all were able to create your tables here, and that is working, and you have all of that working. You can have the partitioning there or not. It doesn't matter. It doesn't matter that much because like we will be able to still illustrate the point of this. So you saw how like we had our we talked about this like sorted DF, but we're gonna go back to just DF here, and we're gonna essentially do a couple things here. One is like we're gonna repartition. We're gonna have 4 partitions here because we want to talk more about like when we write our data out. So with this first one here, we're gonna do a sort, and we're gonna do sort within partitions, and we're just gonna sort on like we're gonna sort on event date, browser family, and host. We're gonna do all 3, and then the second one here, we're just gonna sort on event date. Those are the only 2 things that we're gonna do differently here. And I don't think we need this line. I don't think this is needed. Because we have start DF. Okay, so actually no, this one is not even needed at all because we're not writing here. So we're comparing these 2, right? So one of these has this like event time, right? And then it's not sorted, and then the second one is sorted. One second, I want to drop these real quick. So we say drop table. Can we drop? I want to drop these because I want the number of partitions here to be like based on the date. So can we like run this? Oh, you can only run 1 command at a time. It's so annoying. Okay, because you guys don't need to do this because like you already like have it working. So let me cut this guy. Run this, and then run this. Run this. Okay, so now we have it all partitioned up, and we're going to run this repartition line again, write everything out. Great. Now in this line, line 21, we can look at the file sizes again. Well, this didn't actually finish, I guess. Like that doesn't make sense that it's still only 4 files, because now they should be partitioned on more, because this is bootcamp.events sorted. How does that work? Why is there only 4 files? Interesting, because there should be, I guess, dates here, and because that's interesting. But okay, anyways, like I want to talk more about how this works, because I think this query is probably really crazy to y'all, because this is one of the ways that you can actually look at the sizes of your data sets, right? So in Iceberg, after you write your tables out, you can then query them. Like you can query so you see this is like demo, this is like and then you have your this is the highest level, then you have bootcamp dot events sorted, this is the table, and then dot files, this is the metadata of that table. And like for example, let's just like run something here that is a little bit simpler, like kind of like a select star here, and you'll see, okay, so this is going to be the files that we have written out. And this is going to be all of the kind of data sets. Oh, interesting. It's because it's saying event date is like null. Is it because I don't even have event date up here? Oh, yeah. Okay. Event date's right there. It should be there. Okay. Well, apparently it's saying out there it's always none. But is that the case then? Hold up. Because if we do a select star, is there like a bug in this? It's like, because it's like, no, okay, event date is definitely there. It's right there. It's totally there. Okay, it's fine. It's just like weird that it's not writing it out the way that you would expect. Because like there should be a lot more files. There should be one file like per partition. Because see, the partition here is saying that like they're all like none. And oh, because did the table not actually get dropped? I think the table must have like not gotten dropped or something like that. So what I want to try here, I'm just going to try something real quick. I'm going to put V2s on all of these and just make brand new tables, because Iceberg can be weird sometimes. Okay, so we made brand new tables, and then we're going to put V2 on all of these, and then we will see if that does the thing I'm looking for. So now if we run this line of code, we should get way more files. What? That doesn't even make sense. Like there should be way more files here than just like okay, but see, this actually gives a lot of like metrics about the sorting and stuff like that. But one of the things I wanted to go over with this is you'll see there's like a couple things in here. You see file size in bytes. So you say sum file size in bytes. And then, oh, it's because I was not querying V2. That's why. Wow. Rookie move. These are V2. Okay, apparently it's not actually like there should be more partitioning here than just like none. There should be like it should be based on like the actual like unique values of the date. Because if this is days, right? Okay. Anyways, I don't want to like get caught up in that. Like what I want to show is, because even with this example, like it still has what I'm looking for, and we can still look at it. File size in bytes. And we want to say count one. And then I want to say, and this is as num files. This is as size. And let's go with this. And we want to say, I want to say union all. And then we have events unsorted. Okay. So you'll see here, one of the things that you get here is you see how the file size is significantly different. Like you get like 10 or 15% just by sorting. And the main reason for that is this comes from run length encoding, where if you have all of the low cardinality things together, then you're going to get better partitioning that way. So for example, like let me show you, like if we instead we're only going to sort on date and we're not going to also sort on browser, family, and host. Because I think this is going to give you a kind of an example of how this works. So, okay, that ran. Okay, so now you see how sorting on date was like, it helped like just a little bit. Just a tiny bit, right? It's like the difference between the sizes here is like the same for the most part. So one of the things that you can do here is you really want, like when you're writing your data out, you want your data to be written out from your lowest cardinality first, all the way down to your highest cardinality, like when you're sorting data. So in this case, event date is going to be the lowest cardinality because there's only going to be like a couple hundred records there, and then you have browser after that, and then probably host. There's other ones in here that you could probably put as well. There's like OS family, other things that could possibly, like, you can kind of play around with this stuff. And this is something that you should definitely do when you are kind of like working with writing your data out. And you'll see, okay, so you see, but in that case, OS family was not nearly as good as host when you're writing out, right? Because it was like, what, it's 2 million, 2.9 million. And then what is it here? See how this is like 2.8 million? You get like a significantly bigger size reduction when you're sorting and writing data out with start df, and like you get a better compression from the run length encoding, and you can kind of shrink your data down this way. And like if you care about stuff like this as a data engineer, like you're going to make way more efficient pipelines. Awesome. Well, everyone, thanks for coming to today's lab. Congrats on making it to the end of Spark Basics. Make sure to like, comment, and subscribe, and keep crushing it. I know you're going to get through the rest of this boot camp.